I'm going to introduce my ERC research project called Intranet of Neurons. What is exactly about Intranet of Neurons? To put a simpler explanation, I'm about to build a very tiny Wi-Fi for neurons in the brain. Professor Kaku, a theoretical physics from College New York, mentions in his book there are two greatest mysteries in all of the nature. The first of them is the universe. There are 100 billion planets in our galaxy and 9 planets in the solar system. We just start exploring the universe. We can use very advanced telescope to observe the universe from Earth, but we can also learn more by sending the spacecraft to the planet. Just last month, we have a rover, Perseverance, landing on Mars, starting its journey to understand better the planet. This is definitely not a simple mission. Over several decades, humans have developed capabilities to send these rovers to Mars, with many advanced technologies which we learned from the past failure. One of the most important missions from these rovers is to take good pictures on Mars, like shown here. The quality of camera image need to be high definition, so we need 3D stereo image and 360-degree field of view, as shown here. And at the moment, there are 7 cameras on such Perseverance Mars rover. Although these camera image are high quality, the biggest challenge is actually how to send back this image to Earth. Due to the limited energy source on these rovers, the data rate, meaning how many bits they can be transmitted, are typically limited on this rover. And the radio transmission distance is also a problem. I believe most of us now are using Wi-Fi to join this meeting. During the lockdown period, sometimes I also need to fight the Wi-Fi bandwidth with my wife and my son. But worst case is that we can still use mobile smartphone like 3G, 4G, or even 5G for the internet connection. Currently, the wireless communication infrastructure is so mature surrounding us, we take them for granted. This is not the case for extreme environments without any infrastructure, like in Mars. If Mars rover directly send the data to Earth, for example, in this case, the signal received from the Earth network will be very weak. So rovers need to spend huge amount of energy to transmit. This will use up very fast the very precious energy of the rovers. And the weather condition might also be unstable on Mars, which makes the transmission condition unreliable. Instead, for the typical case, these rovers will send the data to Mars orbiter, Reconnaissance, and Odyssey, shown here. This orbiter have large solar panel, which will not be blocked by the weather condition on the surface of Mars. So they can receive more solar energy and transmit for longer distance. But they are orbiting the Mars quickly. So each day there is only around 5 minutes to 10 minutes of time window. These rovers can upload all of the image data to this orbiter. There are still many engineering problems to be optimized, like what is the frequency, what is the direction of the antenna need to be aligned, etc. But one important thing is that if we lost the radio communication, we will lose the control of the rovers, and we also lost these high quality images. The huge effort for sending rovers to Mars will become useless. Now I would like to stop the Mars part, as that is the focus of ERC. The key point I want to make here is that radio communication, although they are invisible, They are critical for wireless sensing in extreme environments. Now, let's talk about the second biggest mystery, the object sitting on your shoulder. Our brain has 100 billions of neurons, which is similar to the number of planets in our galaxy. Each neuron has even 1,000 connections to other neurons, leading to unimaginable interconnect network. Our brain gives us a feeling that we are an independent and unique individual, but we have very little idea about how it functions. In order to understand better our brain, we also develop many technologies. So one technology that the neurologists like to use is an image method called functional MRI, fMRI. It provides color image on which area the brain are currently active. It gives us a macro view on how brain operates, but it does not provide details. This is similar to use advanced telescope to observe the universe. Something happened there, but we are not sure what is exactly happened. I want to share one example from my neighbor, a lady in her ages of 60s. She had feeling of burnout already for several years. And just a few months ago, she suddenly asked her husband how to insert the bank card to the card reader after she was using that for more than 10 years. So they arrange the check and they have a fMRI scan together with several behavioral tests. And what the neurologist can tell is that there's something happening in her front part of the brain. But there's not much more information about what specifically caused it and what they can do with this image. To know more detail, similar to having rovers on Mars surface to take pictures, we can implant neurosensors on the surface of the brain. This allows us to really record the activities of neurons, the basic unit of the brain. One neurosensor that is approved by FDA in the United States is Utah array. It is electro array with many microneedles. They will be placed on the surface of the brain. It can record activity down to single neuron precision. The downside of this Utah array is that it only has 100 electrodes, or we can say 100 pixels. This limits the number of neurons can be simultaneously recorded. Another limitation is the spatial resolution. The distance between two pixels is around 400 micrometer, which is around 10 times larger than the typical distance between two neurons, which is in the order of tens micrometer. One very important trend in neurotechnology is the number of pixels of such neurosensors grow exponentially in the past decade due to a strong demand from neuroscience and neurotherapeutics. As you can see from the data collected by Stevenson Lab, the number of neurons that can be recorded simultaneously is double, which is equivalent to the number of pixels or of neurosensors, doubles every 6.4 years. It is the neurotechnology version of Moore's law. And the most recent high-resolution neurosensors is actually coming from IMEC. IMEC's NeuroPixels has up to 1,000 pixels, and the spatial resolution is reduced tens of micron by leveraging IMEC's advanced semiconductor technology. This matches the distance between neurons, which such high pixel count and high spatial resolution. The sensors become more like a camera, which provides a high-definition map of neuron activities. One professor from New York University, Bazaski, mentioned in his talk that IMEC neuropixels is the Lamborghini in neuroscience community. If you want to publish paper in Nature, you need to buy this neuropixel. Many of these neurosensors have a common problem, is that they need to send out the data through multiple wires. This makes them very invasive when implanted to living animals or even humans. So here's currently the setup if we want to use such neurosensors for preclinical experiments on animals. Due to the lack of wireless communication, large part of the skull need to be removed. This increased invasiveness of the brain surgery. In addition, the wires that connected to the external computer also limits the behavior of the animal. There are wireless communication developed for primate use based on head-mount stage and Utah array. These head-mount devices are fixed on top of the skull using screws, and there is wires penetrating multiple layers of the tissue to connect it to neurosensor on the brain. You can imagine such head-mounted device can have high chance of accident if it was bumped. And the monkeys will also try to take it off. They cannot be used for longer term because this penetrating part can have high chance of infection, tissue damage, etc. So far, the number of pixels using Utah array is limited to around 100, which do not provide high resolution information. Few research group further scales up the number of pixels by using multiple Utah array. Then this head-mount stage end up something like this with a huge device on the head. I don't see this will end up in the clinical viable setup for humans. So to make this neural camera minimally invasive and can be chronic implant for decades, we need a radio. The most challenging part is there is a trade-off in radio design, which is to have a miniaturized radio that minimizes the invasiveness and have a high data rate at the same time to send out high definition sensor data. So let's start with the tissue structure around the skull to understand what is the invasiveness. Here is a tissue cross-section from the brain or cortex to the skin we call scalp. In between, we also have several tissue layers, choroid and dura. The dura matter is an important layer with a tough membrane to keep the brain fluid inside, and it is crucial to keep dura intact. Skull is similar to bone, and it can be very thick, up to 1.7 centimeter for certain people. Finally, is a scalp that also prefer to be close to avoid infection. To place these neural sensors, we need to first open the skull to insert the sensors. After placing these neural sensors, it is important to suture the dura, seal the skull, and also close the skin to avoid any complication. The surgery of opening the skull called craniotomy. With the advancement of surgical technology, it is possible to reduce the size of skull opening to few centimeters, called burr hole craniotomy, or even below 10 millimeter with microtwistrio. The smaller the skull hole, the lower the invasiveness. If the diameter of the hole can be reduced to below 8 millimeter, then the patient can recover much quickly in few weeks or even days. Then let's switch the direction to look at how much data is needed, the data rate is needed to send out the high definition image. To understand the challenges, we need to first understand what is neural sensor data. Here shows example of the data recorded from the neural sensors. S-axis is time and y-axis is the pixel number. In this case, we have example of only 26 pixels, but it could be much more, up to thousands. And here is the time when one neuron is active. We call it neuron firing or a spike. Each spike from a certain neuron can be recorded from multiple pixels, and each neuron will have different spike waveform feature as shown here. It is important to send out all of this detailed feature for further analysis. Hence, the sampling rate or equivalent frame rate in the camera need to be up to 20,000 frame per second. Assuming we have high definition neural sensors with 1,000 pixels and each with high frame rate of 20,000 frames, to send out all of this data, a conservative estimation on the radio data rate will be up to 200 megabit per second. Just give you an idea how fast it is a data rate the Wi-Fi router at home we are using that can reach when they are in the very optimal condition. With this data rate, you can download a high definition 2-hour movie in just 1 minute. So on one hand, we want the radio to be millimeter scale, and on the other hand, we want the data rate as fast as our Wi-Fi router. Unfortunately, there is a physical constraint in radio design, the trade-off between the size and data rate due to the property of electromagnetic. Here is a survey plot with several implantable radio showing data rate and module size. You can see a general trend that the higher data rate, the larger the radio size. Worth to mention, one radio developed by IMEC was presented last year. Now we want to further push that towards here. So this is several order of magnitude of improvement. So how can we achieve that? This is exactly this ERC research is going to explore. The answer may already within our nervous system involve already millions of years. The first inspiration, let's see how our neurons propagating signals. We all probably still remember basic physics of current flow from ions when they apply voltage. When we apply the voltage in a salt water, for example, with 2 electrodes, the ion with positive charges will move toward the electrode with lower voltage or potential, and ions with negative charges will move toward the higher voltage. This creates ion current flow. On the neural surface, there are many ions with both positive and negative charges. By driving the voltage to a neuron, in this case can be a spike, ions will flow and this can propagate a spike from one neuron to another neuron. Neurons are very tiny in the order of tens micrometer, but they can drive the ions to move or create a current without requiring antenna or even wires. And these ions can actually move quite fast, which means there may be high bandwidth to achieve high data rate transmission. We believe we can use such mechanism for sending data to overcome the physics constraint of the radio between data rate and size. A second inspiration, let's see how the neuron process the information. I want to especially use a retina as example. Human retina has equivalent 500 megapixels. Think about iPhone 12 camera, only has 12 megapixels. So this is a very high definition visual sensors. And it can cover light condition from very dark night to bright outdoor sunlight. So this is supposed to create a huge amount of video data, approximately 1 terabit per second. By the way, tera means 12 zeros. And most of us may have a cable internet, but that is up to roughly 1 gigabit per second, which is still 1,000 times slower than what is needed to transfer this data. So how come the nerve bundle, the nerve optic nerve linking between the retina and the backside of the brain does not get congested? In addition, just transport this can consume thousands of watts of energy. And the whole human brain just consumes 20 watts. There must be something we can learn. Actually, the image we are seeing now is not the original data sent in from the retina. It is more like such kind of image. Each pixels only responds to the changes in time, and it is our brain interpreted such weird image to the normal image we think we are seeing now. This is a video taken by my colleague using an event-based camera that mimics how retina functions. By removing the redundancy information with no changes over time, we can reduce almost 1,000 information that need to be transmitted. If we use this similar approach for sending the neural sensor data, we only need to send the data when neuron is active. This will increase the capacity of data transfer by several orders. So what can we do with this research, and what does it indicate for the society impact? So first, I would like to discuss the technological intracortical brain-computer interfaces. By decoding the neurosensor signals, our mind can directly interact with external machines or computers. This is a powerful technology that can potentially help many people with disabilities. For example, the lady who lost her control of limb due to neurological disorders in this video, demonstrated by DARPA BrainGate project. Let's take a look.
She reached out with the robotic arm. She thought about the use of her own hand. She picked up that thermos of coffee, brought it close to her, tilted it towards herself, and sipped the coffee from a straw. And that was the first time in nearly 15 years that she had picked up anything and been able to drink from it solely of her own volition.
There was a moment of true joy, true happiness. I mean, it was beyond the fact that it was an accomplishment. I think an important advance in the entire field of brain-computer interfaces, that it was really a moment where we helped somebody do something that they had wished to do for many years.
So one thing you can notice is that there is actually a big device attached on her head, which has wires connected to other part of the computers for decoding. Currently, this is one key bottleneck to translate this brain-computer interface technology into clinical use. So We have 100 billion of neurons in our brain. So scaling up the number of recorded neurons is crucial for the brain-computer interface for clinical use. But the question is, how many neurons need to be recorded? No one has an answer until we really have a high channel count brain-computer interfaces. There are researchers from Stanford University trying to estimate this. It is estimated that the number of neurons need to be decoded increase exponentially with the control dimension. So, as shown in the previous video from BrainGate, the state-of-the-art brain-computer interface that can help the patient for grasping is decoding from 100 neurons simultaneously. If we can, you want to restore the limb movement to perform finer movement, for example, tying shoelace, then this will require more than 10,000 neurons recording simultaneously. Even more, to perform full body movement, for example, control exoskeleton, will require even more than 100,000 neurons recorded. With new wireless technology, we can scale up the sensing pixels of the brain-computer interfaces by connecting multiple neural sensors and form a wireless sensor network. This does not require to have a big head-mounted device as used in the primate experiments we showed before. This is also the aim of Intranet of Neurons. In the longer term, we also want to contribute to the evolution of assessment and treatment of neurological disorders using this wireless neurosensing. Up to 220 million people in Europe suffers from neurological disorders, which is more than the whole population of Germany and France added together. Due to the technology limitation and lack of knowledge on how human brain functions, many mental disorders can only rely on psychological evaluation, which at times can be subjective in diagnosis or treatment. I want to end my presentation with one story and maybe also some further discussions. A terrible story happened in 2016 in Taiwan. A 4-year-old girl with the nickname Little Lightbulb was brutally decapitated on the street when her mother was just 1 meter away. It was done by a man with schizophrenia, a mental disorder, or sometimes we call psychopath. Taiwanese society was so shocked and angry, and they want the court to put the killer in death penalty. When he showed up in the public, he need to wear kind of helmet to protect him from being attacked. One big debate was the killer's mental condition was obviously unstable, but the diagnosis was unable to conclude before the tragedy. But due to many complicated factors in psychological misdiagnosis. In fact, many people with mental disorder can be self-aware or unsure of their mental conditions, even if it's already in a very severe condition or deeply suffer from it. One question that worth to think about from this example: will the future neurosensing technology be able to improve the objectivity of psychological evaluation and help the patient to be better aware of their mental state before it is too late, or even to assist the treatment? There is still a very long way to go. I wish my ERC research developing this miniaturized and high bandwidth wireless technology for neurosensing can contribute a small step to this. So this is the conclusion. So first, I show you same as sending Mars the image back to Earth. High quality neural data will only stay inside the skull if there is no high quality wireless communication. One biggest challenge in developing such wireless communication is there's a physical constraint between radial and size trade-off. So high bandwidth and miniaturized wireless technology will contribute to the evolution of clinical viable brain-computer interfaces and also future brain implants as assessment tool for mental disorders.